first time we'll really be able to probe this era where the galaxies first formed. Now, the final thing I'd like to talk about is very different. This is a very versatile camera because we've engineered into it a large number of filters. It carries 80 different filters and prisms in it. I think that's more than any instrument ever in the history of astronomy. And astronomers are very clever in the way they can use these to do different kinds of science. And the example I'm going to give you here is really very close to home compared to the things I've been talking about so far. It's a study of what we call the Kuiper belt. Now, the Kuiper belt is a group of very small objects that surround the solar system. We call these things also dwarf planets, and it turns out that Pluto is an example of a dwarf planet. And the reason it got demoted from its former stature as a planet was because there's so many of these other things, these dwarf planets in the Kuiper belt. And this next picture shows you where the Kuiper belt is. It's way out at the edge of the solar system, beyond the orbit of Neptune. And in the last 10 years, we've discovered hundreds and hundreds of these objects out there. Now, the reason these are interesting and important is that on their surfaces, they carry a frozen history of the early solar system. The way planetary fragments came together and then dispersed, and so forth, back there before perhaps even the Earth was formed. And by looking at these with special filters in our camera, you can do things like determine the relative strengths of water on the surface of these planets versus methane on the surface of these planets. And that's one of the programs that will be undertaken in cycle 17. So it's a completely different kind of thing than, people think of Hubble as looking way out in space. It certainly does that, but it can also look close to home. So we're looking forward to a large number of scientific discoveries coming out of this camera. I can't tell you, what they're going to be in advance, but I can tell you that the potential for good scientific discovery with this instrument is simply outstanding. And now I think I'll turn it over to Jim Green, who will talk about the spectrograph.
Thanks, Bob. Well, I'd like to talk about the cosmic origin spectrograph. And the first thing I want to point out is that it's not a camera. So it doesn't have pictures like you've just been seeing or that you're so familiar with Hubble. It, in fact, is a spectrograph and measures the light from a particular object and breaks it up into its colors. And this gives us a lot of detailed information about the object producing the light and all the intervening material that the light passes through on its way there. And to give you an example, we divide the light up with each exposure into about 6,000 different colors each time we look at it, and not just a handful of filters, but we only look at really one object and all the material along a particular line of sight. So it's a different way of gaining the information about the cosmos than a photograph, and together the images and the spectroscopy give us a very complete picture of all the physical processes that are going on, and they're both really required in order to get the full picture. So one of the most exciting ways to use a spectrograph is to probe gas that would otherwise be invisible because it doesn't produce very much light or no light at all of its own, but objects, light passing through them is affected by that, and we can measure that effect and get a very detailed understanding of the gas. And in particular, COS wants to look at the gas in between the galaxies in what we call intergalactic space and understand how that gas is distributed, what's out there, how did it get there if it's not in galaxies. Is it there from the Big Bang? Has it been put out there by processes afterwards? So this is one of the basic questions, and Dave alluded to it earlier in the architecture of the universe. And in this first video, which Dave also showed, but I'll give a little different commentary on it, is talking about the evolution of structure. So this video shows material condensing, starting at the very earliest parts of the universe and collapsing into these filamentary structures. It ends at the present day. And I want to emphasize this is a simulation, a numerical simulation of what we think is going on. But the thing to notice is that it forms a filamentary structure, and that most of the gas in the universe is actually involved in these filaments, but it's spread out over huge volumes of space and is a very low density. And we'd like to be able to understand, is this really what's going on? This structure is the result of sort of the forces of gravity trying to cause all matter to collapse and the expansion of the universe causing it to expand. And most of the mass of the universe is in dark matter, and the expansion of the universe is dominated by the dark energy. And so all that plays into this picture of what does the actual structure of the universe look like today. So what we want to do, the next video I have queued up here is a simulation like the last one, but a much more detailed one. And I'm just going to sort of examine the video as the structure of the universe appears today. This is known as the Millennium Simulation, and over 10 billion different particles of matter were simulated and evolving through time. And so this is a spatial zoom in on a particular time in the history of the universe, i.e. today. And the scales, an MPC, that's a megaparsec, that's about 3 million light years. So even as we zoom into this smallest scale here, we're still talking about the size that's larger than a cluster of galaxies. The distance between our galaxy and the nearest galaxy is about 1 megaparsec. So, and as we zoom out, you can see this structure that comes up. And this is what we refer to as the cosmic web. I think you can see why it's been coined that term. And we would like to be able to examine that in great detail. Now, the problem is that these filaments produce very little light. And so you can't just take a picture of them. Otherwise, we would have done it a long time ago. So instead, we examine them spectroscopically by looking at very distant objects that are further away than these filaments. And as the light travels across the billions of light years to the Earth, it passes through regions of void where there's no filaments and then passes through filaments. And as it does so, the light interacts with the gas in those filaments, and certain colors of light are absorbed out and others are passed through. And this leaves a very recognizable footprint in the spectrum of the object that we know how to analyze, because we know that the hydrogen and the oxygen and the carbon way out there, billions of light years away, is the same as the hydrogen and the carbon and the oxygen on Earth, and we understand the patterns that they impose. So this next video shows the fundamental experiment we want to do with the cosmic origin spectrograph, which is to probe this structure by looking at distant objects. So in this video, you can see a quasar out there making the light, and as the light travels through the cosmic web and passes through filaments, the spectrum, represented by those little colored sort of prisms, and the dark lines being the effects of the gas, create a recognizable, I'll call it a fingerprint, in this spectrum that lets us probe where those filaments are, how much gas is in them, their chemical composition, their temperature, the speed at which they're moving. All these things we can actually get out of this. Now, of course, one particular observation like that is very interesting, but in order to start to understand the large-scale structure and build it all up, we need to have many such observations, lines of sight through the universe, and so we need to be able to observe hundreds, even thousands of these targets. And that means we have to have a spectrograph that can see extremely faint objects, because there just aren't that many bright objects that are billions of light years away that look bright to us here on the Earth. And so COS was specifically designed to do this experiment by increasing the sensitivity compared to the previous Hubble instruments. So COS is about 10 to 70 times more sensitive than the current Hubble instrumentation. What that means is that we can either look at an object that's 10 to 70 times fainter, or we can look at 10 to 70 times more objects in the same amount of time. Either way, it enables us to do a true spectroscopic sampling of the sky and really build up a statistical picture of what's going on out there in terms of these filamentary structures. Also, we see them. One of the nice things about astronomy, whenever you look at something far away, you get the history of the universe in one picture. So remember, if I'm looking at something that's 2 billion light years away, I'm seeing it the way it was 2 billion years ago. And so as I build up these long sight lines, I get the history of the universe laid out in front of me. Are the filaments close to us different than the filaments far away? That would tell us that the universe was different in the past. And how was it? We know it was different, but we want to be able to quantify those sorts of questions and the kind of processes that were resulting there. Now, obviously, if you get an instrument that can do 10 to 70 times objects that are fainter than that, then it opens up a whole host of other scientific objectives that people can accomplish. And my colleagues around the world have submitted lots of proposals to use COS to do all sorts of things, not just this cosmic structure question. Some of these things involve looking at interstellar clouds that absorb most of the light of the object, and so the object interior is very faint, but we've never been able to probe those types of clouds, to look at the atmospheres of planets around other stars, to look at young stars in their burgeoning areas right after they're born. And so we have a very exciting program, not just that we're going to execute with the COS team, but astronomers around the world to do that. And the last thing I'd like to point out is that it's an ultraviolet instrument, and the wavelengths of light that it measures, in fact, don't reach the Earth at all. And so this type of an experiment has to be done with Hubble or with a space telescope of some sort, or it can't be done at all. There is no option to doing this from the ground. With that, I'll pass it on to Dr. Hamill, who'll talk about, put it all in perspective.
Thank you very much. You know, when they asked me to do this, I was sort of surprised because everybody else who's spoken to you today has been involved with the Hubble project for years, if not, in some cases, decades. And I'm not. I'm a user. I'm not a Hubble person.